The main focus of this presentation will be the discussion of cross-curricular learning between science and mathematics. We need to acknowledge that cross-curricular isn't a new debate in education, so let's take a look back at the history. The Haddo Report in 1931 endorsed the movement to cross-curricular learning. The report was surprisingly progressive. It argued that a good school is not a place of compulsory instruction. The curriculum is to be thought of in terms of activity and experience rather than knowledge to be acquired and facts to be stored. The report led on to many discussions regarding this way of teaching. The Plowden Report in 1967 has many recurring themes, some which are individual learning, flexibility in the curriculum, and the importance of the evaluation of children's progress. Teachers need to be aware that the knowledge of different areas does not necessarily fall into separate areas, and they can be taught as complementary subjects rather than opposites. The Three Wise Men, Alexander Rose and Woodhead, 1992, state in their report that effective teaching, regardless of the strategy used, requires the teacher to deploy a range of techniques. It is particularly important that the potential of explaining and questioning is realised. There needs to be more sharply focused and rigorously planned topic work for an increase in single subject teaching rather than cross-curricular. The report also states that curriculum practice will improve if there is an appropriate balance of the various cross-subject activities within topic work. Fast forwarding to Rose Review 2009, Rose looked at how primary schools also show that high standards are best secured when essential knowledge and skills are learned. This is through direct high quality subject teaching and through this how the content being applied and used in cross-curricular studies. Primary schools have long organised and taught much of the curriculum as a blend of discrete subjects and cross-curricular studies in this way. It is the best of this work that has informed the recommendations of this review. Firstly, let's begin by looking at what is cross-curricular learning. According to Jacobs 1989, a cross-curricular approach is referred to as interdisciplinary because it incorporates more than a single subject area. The subject disciplines may be related through a central theme, issue, problem, process, topic or experience. It is the use of one subject to support another. So, how can we approach cross-curricular learning? Jonathan Savage 2010 states, a cross-curricular approach to teaching is characterised by sensitivity towards and a synthesis of knowledge, skills and understandings from various subject areas. These inform an enriched pedagogy that promotes an approach to learning which embraces and explores this wider sensitivity through various methods. What this means is the enriched pedagogy of cross-curricular teaching is embraced and explored by the teacher. Teachers will need to ensure that their subject knowledge is secure in all areas they are teaching. As teachers, we are able to develop a cross-curricular approach to learning that utilises a range of methods or techniques to ensure the children are getting the best out of their learning. The rest of this presentation will look at cross-curricular subjects, and an example that I'll be demonstrating is the use of science and mathematics and how they can be taught together. According to McRae 2010, mathematics and science are natural partners, sharing similar goals of building process and problem-solving skills. Driscoll, Lamboth and Roden 2015 support this statement, stating that the application of mathematics is fundamental to many aspects of science. Carrying on, Driscoll, Lamboth and Roden continue with the link between science and mathematics and how ICT can be added on to that package. Computational skills are necessary when pupils are involved in manipulating any data, especially scientific inquiry that involves taking a number of measurements and then finding an average to increase the reliability and validity of findings. When carrying out a science lesson, one that naturally involves mathematics, it is the science that is being assessed, not necessarily the children's mathematical knowledge. This is where ICT can be used. The impact of ICT in schools goes beyond the pedagogical and has the potential to affect many other aspects of school life, from altering present teaching practices and providing the opportunity for teacher development to improvements in the quality of the learning environment. A science experiment that I'm going to look at is the mass of the fruit past or before and the mass after it has been dissolved in 50 millilitres of boiling water over a 2-minute period. Instantly from this you can see that this experiment will hone in on math skills. After collecting the data for the experiment with the use of ICT and programs like Excel, you can create a variation of different graphs to see what is most suited to show your data. It is used to support their learning, not necessarily enhance it. Rather than get the children to use their mathematical skills and draw the graphs themselves, because by this point in their learning, this knowledge will already be secure for them, they are able to create graphs using ICT instead, saving time and allowing them to explore more into the scientific aspects of the experiment. As the independent variable is categorical and expressed in words, then the bar chart is the best option for this experiment. The Maths National Curriculum backs this up by stating pupils both encounter and draw graphs relating to two variables arising from their own inquiry and in other subjects, an area that this investigation has covered and one that promotes cross-curricular learning. Best teaching was also characterised by assessment of understanding and skills including analysis and interpretation, where pupils were involved in carrying out and evaluating the investigations. Ofsted 2013 state that by allowing children to analyse the data and the graph types, it is a key learning skill and one that is relevant to the national curriculum. In the national curriculum, it says recording data and results of increased complexity using scientific diagrams and labels, classification keys, tables, scatter graphs, line and bar graphs. The Science National Curriculum also has a lot more ties within mathematics. As part of the Upper Key Stage 2 National Curriculum, when working scientifically, it dictates that children need to use test results to make predictions to set up further comparative and fair tests. For a science test to be fair, it must ensure that the test is carried out 3 or more times to remove any anomalies. The Maths National Curriculum 2014 states, at the same Upper Key Stage 2 level, children need to calculate and interpret the mean as an average, something that was carried out before presenting any final data. These two key areas of the national curriculum work side by side, which leads to effective cross-curricular work. When allowing children to create their own fair tests, we need to regularly assess what children know and have learned. This will help to ensure there is continuous progression. As we can see here, that the links between maths and science from as early as Key Stage 1. In more recent studies, Ofsted 2010 found that pupils with widely differing abilities and interests were fully engaged and appropriately challenged. This supports the argument that cross-curricular work fosters a child-led approach, and that an advantage is that activities or topics can be changed or adapted in response to the interests of the children or to current events. Ofsted 2013 also state that the children learn best when they see how the science they were studying is linked to real-world experiences. It revealed more about the big ideas in science and connected with and supported learning in other subjects, including mathematics. Learning in this fashion was said to engage and enthuse pupils, developing their natural curiosity and motivating them to find out more. So we need to look at if teaching in a cross-curricular approach is the most effective way. So let's weigh up the pros and the cons. Wrigley et al. 2012 states, many teachers see cross-curricular approaches as motivating, enjoyable and capable of building relevance and meaning into the curriculum. Looking at cross-curricular pedagogy, Alexander 2000 suggests that children's learning should be tied to existing learning experiences, multisensory activities, social settings in which language is used and ample opportunity to follow what naturally interests them. Cross-curricular pedagogies are better placed to motivate, sustain, be meaningful and socially satisfying than a curriculum purely devoted to separate subject teaching. Each item on Alexander's list implies some form of cross-curricular approach. With seamless links between assessment and good quality learning, there is an emphasis that cross-curricular learning is more effective. Linking this back to cross-curricular maths and science, Haylock 2010 states that pupils should learn how to collect data as part of a purposeful inquiry. The skills of handling data and pictorial representation are best taught this way, relating to topics focusing on other areas of the curriculum such as science. On the other hand, making connections between subjects has become controversial. The Department for Education 2013 omits reference to cross-curricular links, and Hurst 2006 supports this by arguing for a pure knowledge curriculum by continued subject separation. Cross-curricular is not without its dangers. A main reason is the tenuous links were often made between too many subjects, or subject record keeping or progression was almost impossible. This can be seen as a reason why the Science Acts were abolished back in 2009. Murphy et al. 2010 noted that some reasons included reduced stress and pressure on the children, better learning and teaching in science, and more time for the other subjects. Since 2014, levels have now been taken from the other core subjects, so learning targets remain even more vital now there are no science sets and no levels in maths or English. Progress is not easy to manage, even when two subjects are involved. In a critique of cross-curricular teaching and learning, Hayes 2010 points out that advocates of this approach argue that an emphasis on discrete subject teaching creates artificial barriers in younger children's minds, and consequently they fail to make a secure connection between different areas of knowledge. Going back again in history, looking at the Haddo report and the Plowden report, even though these reports have been influential in the teaching of cross-curricular, they do however recognise that in the hands of teachers who do not have the relevant subject knowledge, cross-curricular can be counterproductive. However, after 2010 have noted that there are no necessary conflicts between single subject learning and cross-curricular learning. Both can exist profitably side by side. When looking at assessment, Barnes 2011, like Taylor 2011, make a strong case for the using the principles of assessment for learning, where the assessment is informed by the teacher's knowledge, among other things. Good practice in assessment stems from careful planning and having clear learning objectives. With careful consideration, they suggest it is possible to assess children's learning from two or more different subject perspectives. To conclude, as noted in the Rose Review 2009, subjects offer one way, though again not the only way, of translating what is learnt and taught into a curriculum which is manageable on a day-to-day basis. There are times when it is right to marshal content from different subjects into well-planned cross-curricular studies, but also because it provides opportunities across the curriculum for them to use and apply what they have learned from the discrete teaching of subjects.